All right, chemists, welcome back to Chemistry 132B. We are doing lecture 6 today, and we are going to pick up where we left off on Wednesday. If you remember, on Wednesday, we looked at a wave function, let's say an electron that's moving through space, and the wave function of that particle, we were trying to find mathematical descriptions for. We saw that the complex exponential is a valid solution of the Schrödinger equation in that case. And then we also started to put some barriers in front of our particle, a potential barrier. And we noticed that the wave function takes on a different form in the barrier, but it doesn't completely disappear. That's what we noticed last time. It doesn't completely disappear in the barrier, even though the particle has less energy than the energy height of the barrier. Okay, so classically the particle would not be able to get in there, but quantum mechanically it can, and that is a phenomenon that's called tunneling. Okay, so that's what we saw last time. But the barrier that we encountered was a finite barrier, meaning that the potential energy barrier did not have an infinite value, it had a finite value. So today we're going to look at a situation where the particle is moving in space. Okay, so we assume we have quite similar solutions to the ones from last time. But now we are going to put barriers on both ends. Okay, so two barriers, one on the left and one on the right. So the particle is caught in between. And then we're going to raise the height of the barrier to infinity and see what happens. So that's kind of like on the menu for today. Before we do that, I'd like to show you a couple of things that we need to kind of like really be aware of before we move on. That's kind of complex calculus. Okay, so most of you are familiar with complex calculus. We're not going to do very high level complex calculus, but we do need to know the basics in order to appreciate some of the derivations that are relevant in this course. Okay, so let's get started. I'm going to start with writing down basically one of the definitions of the complex number I, and you are probably familiar with the fact that the square of I equals -1. Okay, so that's hopefully something you don't see for the first time now. If I take the square root of both ends, both sides, I see that I have I equals to the square root of -1. Okay, so that's another definition of what I is. So that means if we encounter a negative value and we are forced to take the square root of that, we don't have to say that this is impossible. We can now work with the imaginary number I. And that means if I have an arbitrary number, let's say A, and it is negative, and I'm going to take a square root of that I can always write that as basically I squared times A and then the square root. Okay, and so that means that I can write that as I can write that as I square root of A. Okay, so that is kind of a very useful trick that we apply in this course several times. Okay, so a general number that is complex is written as follows. Okay, this is the most general way of writing it. So the complex number is called Z, and it has a real part, which is typically indicated by X, and then there is an imaginary part, which is indicated by Y. Okay, so a number could be complex, meaning that it has probably both a real part and an imaginary part. Sometimes X is equal to 0, then the number is completely imaginary. Sometimes the number Y is 0, and then the number is completely real. But in general, for complex numbers, X and Y are non-zero, and so they have both real and imaginary components. So the real part of this complex number Z equals X, and the imaginary part of the complex number Z equals Y. Those are definitions, right? For us, what is important is a very well-known quantity, and that is the complex exponential. Okay, so we write it as follows. This is a complex exponential, as you can see, because there's an I there in the power, in the argument of e. And we can write this, and this is something that is it's a beautiful formula, really. I think it was Euler who kind of came up with this. We can write that in terms of a real part, okay, cosine x, and then the imaginary part, which is the sine of x. Okay, so the real part of this complex exponential is the cosine x, and the imaginary part of this complex exponential is the sine contribution to the number. Okay, so this is an expression, the complex exponent written in terms of cosines and sines is something that we will use in this course. Okay, so this complex exponent has some really interesting properties. Okay, and so one of them is the following. If I take this number and I take the modulus square of it, okay, so if you write that out, that means that you multiply it by itself, but with the complex conjugate. That means that the I now gets a negative sign in front of it. Okay, so that's the definition of modulus square. And I can rewrite this as ix minus x. Okay, so basically that equals e to the power 0, and that equals 1. Okay, so complex exponent, the modulus square of it, no matter what x is, if you take the modulus square of a complex exponent, you get 1. Okay, very interesting property. So another very interesting one is the following. The argument now is I to n, where n is an integer, any integer, times pi. Okay, so this equals 1 for n equals an integer. Okay, so that is also very, very nice, because basically this complex exponent, which is a complex number, but in fact, it is purely real. Okay, so it does not have an imaginary part. You can actually verify this quite easily. If you use the expression on the previous slide, where it says that a complex exponent equals a cosine plus I times a sine. Okay, so if you put that argument in a cosine and in a sine, you see very quickly that the sine contribution is going to be 0, and the cosine contribution yields 1. Okay, and by the same mechanism, you can prove quite easily that the following expression equals minus 1. Right? So I times 2n plus 1. So basically, between parentheses, you have an odd number, an odd integer, times pi. If you substitute that number in the Euler equation for the complex exponent, so the cosine and the sine, put the argument in there, you can quickly see that the sine, again, is going to be 0, and the cosine is going to give you minus 1, sorry. Right? So this is a good expression to keep in mind. Okay, now finally, given this expression, let's write it down one more time because it's so important. For the complex exponent in terms of the cosine and sine, I can now write the cosine and the sine in terms of the complex exponents. Okay, and these are the following famous formulas. The cosine is half e to the power x plus e to the power minus ix, e to the power ix plus e to the power minus ix. That's the definition for the cosine. And the sine is quite similar, but a little different. Ix minus e to the power minus ix. Okay. So this expression we will in fact use today. So today we'll be using this definition for the sine in order to clean up some of our math. Okay, so I hope this is not the first time you see this. If it is, then hopefully bear with me, and you'll be able to apply it in some of the steps that we will be doing today. Okay, so let's look at a slightly different scenario here, namely a molecule. And the molecule I'm going to look at is the following. It is the retinol molecule. Okay, here it is. It's a very nice molecule. Okay, it's an important part in your diet, in fact. Retinol and retinol are closely related, and retinol is the molecule in your eye that enables you to see. Okay, so that's the molecule that absorbs the light that you are experiencing when you use your eyes. So here's a retinol. Okay, there's an hydroxyl group right there at the end. And we see immediately that what is so interesting about this molecule is that it has multiple double bonds. In fact, these bonds are conjugated. Double bonds are conjugated. Okay? And you know, of course, from all the other chemistry courses you've taken that an electron that's involved in this pi network can move almost freely over this entire length of the conjugation. Okay, so why is that important? Well, we know, and this is something we have been hammering on now for a while, that the electron, in fact, has wave-like properties. So when the electron is stuck in a finite region in space, these wave-like properties will be very important. In fact, the electron will behave mostly like a wave rather than behaving like a fixed particle. Okay? So we have to include the wave-like properties of this electron. Now, the electron is now caught in a small region in space, namely over this length of the conjugation. That is the length over which the pi electron can freely move. Beyond that, it can't. Okay, so why am I saying this? Because what it basically means is that I can raise some barriers in the following way. Okay, I can say, look, the electron is the pi electron, not all the electrons, of course, only the electron that's part of the pi conjugated network cannot move beyond this bond, okay, because beyond here is no conjugation. So all the way on the right, there's a barrier for the pi electron. It cannot move beyond that point. And so effectively what I'm saying is the barrier is so high, I'm going to make it infinite. So V equals infinity, such that there is really no way that the electron can move there. So I'm confining it. I'm confining the electron in a finite region in space. And the same is true on the other end. Okay, you can see here it makes a little bend, okay, just before this barrier on the left, but it doesn't really change the story here. There is still a barrier. The electron cannot move into the ring. Okay, it can't. It just is fixed here in this kind of like quasi one-dimensional path that it can take. So what I can do now is I can model this problem as a particle that is caught between two walls. Okay, and the walls are infinitely high in terms of their potential energy. So this is what I can do. I can now just make a one-dimensional model between the length x equals 0 and x equals L. That is, again, the length of the conjugation length, okay? So that basically spans the entire pi conjugated network in a one-dimensional situation. All right, so the particle then, if I think of me being a pi electron in this system, I'm caught between these two walls, and I can move only in the dimension x from 0 to L. I cannot move into the barrier because the barrier is infinitely high. So what do I have then for the wave function in these regions in space? Well, we know that the general solution of a particle that is moving in free space where the potential is 0, and this is important to realize. I want to make sure you guys understand it. In this region here, okay, the potential is 0. Okay, there is no barrier. Only on the left and the right is the barrier infinitely high. So in this region here from 0 to L, I have the same solution as last time. Okay, that is basically the solution for a freely moving particle, aka an electron. This electron is stuck in the box, but within the box, it can freely move. There is no potential there. Only when it hits the regions here, it encounters a potential. Okay, so what happens in these regions where the potential sits? Well, we actually found solutions last time. Remember that? If it hits this barrier here, I found that this k here becomes complex. So I have minus kappa x. Okay, the coefficients a, b, and c are to be determined. We don't know what they are, but we know the functional form of the wave function in this barrier must take on this shape. That's what we just concluded last time. What about the barrier on the left? Well, the same story, okay? But now it's not minus kappa, but plus kappa, because if you move to negative x, of course, you're going to have a negative sign in front of it, and it is a decaying function on the left as well. Okay, so the same function on the left and on the right, all right? In the middle, free motion of the electron in the barrier constricted. That's basically implicated by these wave functions that I'm writing. Okay, so now let's have a look at what happens in the barrier. Okay, I'm going to now focus on the situation in the barrier and see what is going on there. So let's look at the definition of K. If you remember what K was, right? K was defined in the following way. Okay, so because K squared was 2m E minus V, that was the definition of K squared. Okay, so E is the total energy of the electron, V is the barrier. Remember that? That's what K was. Now, in the barrier here, we have, of course, a situation because V is very much higher than E. Okay, and that, of course, means that K becomes complex, exactly the same way as we have said before. So I can write that now as I times kappa. Kappa is still positive because that's V minus E, so I make that positive. And then there's a negative sign in front of it. If I take the square root, and of course I get the I. So that's what we did last time. Hopefully you remember that, right? So here's the definition for kappa. Kappa is defined as 2m times V minus E. Okay, E is the total energy, V is the potential energy of the barrier. I take the square root of that and divide it by h bar. That's what kappa is, right? And we know what the wave function in the barrier looks like. It looks like this decaying exponential, right? But now the situation is not exactly the same as before on Wednesday, because now V is actually approaching infinity. What does that mean? Well, that's simple. Kappa is going to approach infinity as well, right? So that means if kappa is going to approach infinity, that the wave function in the barrier on the right is going to be a decaying exponential with kappa going to infinity, meaning that the complex exponent decays to 0. Okay? So that basically means that the particle has a wave function in the barrier with an amplitude of 0. All right? Now, an amplitude of 0, if you take the square modulus of 0, you get absolutely 0. That means the probability, of course, that is what the square modulus is of the wave function, is going to be 0. So there's no chance of finding the particle in the barrier if the potential energy is going to infinity. Okay, so that is basically indicated here in this kind of graph where you have the barrier again. Okay, and I say basically in the barrier, it is absolutely 0. There's no amplitude. Okay, that's what these flat lines mean. That means they're flat, it's 0, value 0. It means no chance, no probability of finding the electron in the regions outside of my defined region 0 to L. It can only be between 0 and L. It can go in the barrier, and the same argument holds for the barrier on the left, exactly the same. Okay, so what I'm left with then is a particle that is stuck, that is basically assuming a wave-like motion, a wave-like shape, and it must disappear at the edges. Okay, it must disappear at the onset of the barrier because the probability there is 0. That means the amplitude of the wave function must go to 0 there. So that's kind of like what I call a boundary condition. Okay, I have a boundary condition because I require, in this case, that the wave function must have a value of 0 at the barrier. That is the requirement that I have for this problem. That's called the boundary condition. Okay, and then the other thing is that we can see from this picture quite nicely that it is a wave-like shape, and so then if I have this condition that it must disappear and reach 0 at the edges, at the boundaries, then only certain shapes of the wave actually fit. Okay, so this is what we call quantization, meaning only certain waveforms are allowed, others are not because they do not fulfill the boundary conditions and therefore are unphysical, right? Only certain shapes of the wave actually fulfill the condition, others do not. And that's very different from a particle in free space, because if you take those barriers away, you can have any shape of the wave function. They're all allowed. There's nothing that determines that only certain shapes are allowed. Okay, so now we have a different case. The placement of the barriers confines the particle and therefore determines that only certain waveforms are allowed and others are not. That is the basis of quantization. Okay, so now let's have a look and if we can determine what this wave function is. Our goal is still to determine what is the shape of this wave function. Okay, can we say something about that? Okay, so let's see if we can write something intelligent about this. Okay, so our goal is to find the wave function. And what kind of information do I have? Well, the pieces of information that I just laid out, right? And that is that the general shape of the wave function looks like this. Oops, that's bad. Come on. The general shape of the wave function looks like this, plus b. Okay, that's hopefully clear now. This is the shape of the wave function in the region between 0 and L, because beyond those regions, the wave function is going to be 0, right? That's what we just determined. We also know that k, the value of k, equals this. Okay, so it's 2me divided by h bar. There's no v here because v equals 0. Okay, so that's really important to realize, because in the box, okay, not in the barrier, but in the box between 0 and L. So for these values for x, the k takes on the value as written, because v equals 0. So there's no potential energy in the expression for k. We also know that if k squared equals the square of this, okay, then I can actually write what the energy should be. Okay, so the energy is going to be k squared h bar squared over 2m. So what does that mean? Well, that means if I can figure out some way, somehow, what k is, okay, if I can find an expression for k, then I also know what the energy is, because the energy depends on whatever k is. Because the rest, h bar squared, 2m, those are all constants. The only thing I don't know what it is k. So if I find k, I have the energy. So I have two things then. I have the shape of the wave function, psi, and I have the energy, the associated energy of the wave function. So that's what we're trying to do. So what kind of information do we have then? Well, we just determined that there's a condition, namely at the location 0, the amplitude must go to 0, and the same is true at the location L. Okay, so that is basically the boundary condition. It's the boundary condition. Okay, so let's try to see if we can determine what the wave function looks like with these two conditions fulfilled. All right, so I'm going to say, I'm going to take the shape of the wave function, okay, and that is the following. A times ik0 plus b minus ik0. Okay, so that is not so hard, because that is a, this is going to be 1, the complex exponent with the argument 0 is going to be 1, and the same for the other one. So I get a plus b equals 0. Okay, must be 0 because I just said at location x equals 0, the amplitude of the wave function must be 0. Okay, so that means that I'm confining now the relation between a and b. I can say that b is equal to minus a. Okay, so that means that I can now write a general expression again, but now I have an expression for what b is. So the general expression now becomes this. Oops. Ooh, come on, Eric. Minus a. Okay. Okay, so that's basically the first condition. What is the second condition? Well, the second condition is that if I fill in the value L for x, I also must get 0. Okay, so that means that I get the following condition. This must be 0 as well. Now, here is where we're going to use this kind of trick for writing the complex exponent in terms of the cosines and the sines. And I recognize here that I have, a positive complex exponent and a negative one. The a is the same number, of course, so I can write that as follows. Okay, and that looks like a sine function. Okay, remember the definition in the beginning of the course? So I can write now this in terms of a sine. Okay, 2 times a times I, and then times the sine of KL. Okay, that follows directly from the definition of the sine. So if you don't really remember that, let me put it up here. Make sure that you can see it. Sine of, let's say, KL in this case, equals this function, 1 over 2i times IKL minus IKL minus. Oops, you get the idea, right? There it is. So I use that definition, plug it in, and therefore I can write it now as follows, but the result must be 0. Okay, so that is actually kind of interesting. So I'm asking myself, when is the sine of KL 0? Well, that is not so hard to figure out. And it's 0 every time the argument KL equals an integer times pi. Okay, so whenever this is true, n times pi, you can figure it out very quickly for yourself. Okay, if the argument KL is equal to an integer times pi, then the sine function must be 0. Okay, and that means that K must equal, n pi over L. Okay, n pi over L. So that is a condition that I find now by using these two boundary conditions. All right, so what does it give me? Well, that gives me the following. I can now rewrite the wave function as follows. I'm going to give previously I had 2 times I times A. I'm going to simply call that C, some kind of constant. It's a complex constant, but it's a constant nonetheless, times sine, and the KL with K n pi over L becomes n pi over L times x. Okay, so that is the wave function, the shape of the wave function. There's no unknowns, okay, because L is the length of the box, n is an integer, pi is of course a number, and C is a constant. So C is something that I can determine, but it's just scaling the amplitude. It doesn't change the shape of the wave function. I also noticed previously that if you know K, you know the energy. Why? Because there's a relation between K and energy, right? K squared is in the expression for energy, and I know what K is. It's n pi times n pi divided by L. So if I take the square of that, what I find is n squared pi squared h bar squared divided by 2m L squared, right? That is the expression. And I can now use a little bit of a substitution here. I just simply use a definition of h bar, which is h divided by 2 pi. Okay, I substitute that, and I'm going to rewrite the energy as follows. N squared h squared divided by 8m L squared. So that's kind of my solution here. I have two things. One, the shape of the wave function. It's a standing wave that looks like a sine wave, but it has now an index, n. So the n has values 1, 2, 3, and so forth. Okay? And I also have now the energy, which also gets a label n. Because the n is in there, it's an integer, 1, 2, 3, 4, 5 to infinity, right? And that means the energies take on particular values, right? So if I have the solution wave function n equals 1, I get a particular expression for the wave function, and I get its associated energy, simply substituting the value n equals 1 into the expression right here, right? So I found here my energies and my wave functions. Now, the first important point is what I just underlined, and that is that these wave functions and energies are quantized. Okay, they have a label n that says only these solutions are valid solutions. Previously, we did not have fixed labels. Okay, if a particle is floating in space without any boundary conditions, there is no quantization. every solution is in principle fine. Every value of K is allowed. Here, it's not. Not every value of K is allowed because of the presence of the box and the infinite walls. Only certain solutions are allowed. Okay, so that means the solutions are quantized. That means the particle can only have certain wave function shapes and certain energies and nothing in between. So that's the basis of quantization. Okay. The other thing that I noticed is if I look at the energy and I look at some numbers here, I see that there's the L is in there and it's in the denominator. That means if the L becomes longer, that means that the energy N becomes lower. Okay. And that means that the separation between subsequent levels, let's say between N equals 1 and N equals 2, becomes smaller too. Okay, so the longer L, the longer the box, the smaller the difference between the subsequent energy levels. Right? What does that mean? Well, this is an important kind of concept here. It means that for smaller boxes, okay, very small boxes, like the size of an atom, the separation between allowed energies can be very large. If you make the box very long, the separation between subsequent energies is very small. If you make the box infinitely long, like macroscopic scale, the world we live in, the world we perceive, then the separation between energy states is negligible, meaning it has no quantum character. And that's exactly what we think should happen, right? In the limit of moving things on a larger scale, all these quantum mechanical concepts should disappear and we should end up with a classical framework once again. And that's happening. Okay, the other thing is there's also an M in there. Okay, so that means that if the particle is very light, that the separation between energies is large. Okay, if the particle is having a very high mass, that means that the energy separation between subsequent states is very small. So that's the same argument. If I have a heavy object, then the separation between quantum mechanical states is negligible and it behaves like a classical object. If it's very light, like an electron, then I can have the situation that the separation is substantial and so has a lot of quantum mechanical character. Okay, so these two notions, the weight or the mass of the particle and the length of space in which it is confined are very important ingredients that define the quantum character of the particle that I'm looking at. So there's one more interesting thing, and that is this value of n, because I say the lowest value of n equals 1, and then 2, 3, all the way to infinity. But why doesn't it start at 0? Okay, why is that? Well, that is because if you put in 0, look at what happens to the wave function. The sign of 0 is 0 everywhere, independent of x. Okay, that means that basically this function is going to be 0 in the entire interval x equals 0 to L, everywhere. And if you take the square modulus of that function, okay, it's going to be 0 for every x, meaning the probability of finding the particle in the box is 0. It's not there. Okay, so that's a moot point, right? It's moot because, sorry, it's not moot, it's moot. It's a moot point because if the particle is not there, then there's really nothing to look at. The particle is either there or it's not. And if it's there, the value of the n cannot be 0 because then it's not there. So as soon as you put a particle in there, the lowest value of n is 1. And if n is equal 1, that means that the energy is finite. Look at the expression right here. Okay, this expression right here for energy, there's the n. If you put 1 in there, I have a finite value for En. The lowest possible value of n is 1. That leads to the lowest possible energy that the particle can have. This is what we call the 0-point energy of the particle. It's not 0, okay? So En for 1 is not equal to 0. It's finite. The lowest possible energy that the particle can assume in the box is not 0. It cannot have energy 0. It must have a certain energy. As soon as you put the particle in a box, it assumes a lowest 0-point energy, which is finite. Okay. All right. There was a question. Erin, do you have a question?
Yes. I was just wondering, like, where did this 8 here come from?
So the what? The 8?
Yeah.
Oh, the 8 comes from, look at this formula right here, okay? Hopefully you see that. And then I put in h bar squared. So h bar squared means I have this. Okay,
Oh, I see.
2 pi squared is 4 pi squared, right? And 4
Uh-huh.
times 2 is 8.
Got it. Thank
See
you.
that? Okay,
Uh-huh.
that's a good question. All right, before I continue, I'd like to say one more thing. Let me clean this up. Okay, so I'm going to write down the shape one more time. C sine n pi x over L. That's the general shape of the wave function. And I'm going to ask myself, okay, what is the momentum? What is the momentum of this wave function? So basically, if I operate on this wave function with p operator for momentum, what do I find? And if you do that, you actually find something interesting. This is going to be 0 all the time, all right? And that is basically explained because really this sign, if you remember, is composed of 2 things. It is something that looks like, you know, ikx and ik minus with a minus sign, ikx with a minus sign. Meaning this guy is a particle moving to the right, this guy, and the second guy is a particle moving to the left. So the same situation as before, right? And if you have equal weights of going to the left and to the right, you're not going anywhere. The momentum is effectively 0. And that's the definition of a standing wave. So a standing wave certainly has energy, okay, but has no momentum. The shape of the wave function is not changing as it moves, okay? It stays steady in space. And so the momentum is going to be 0. The average momentum, the expectation value of momentum is going to be 0, even though the particle certainly has energy, right? So that is a property of a so-called standing wave. Equal portions to the left and to the right. Okay. So now let's get back to something that is related to all of this. There. Let's go here. Okay. So, you know, our general, let's say our lowest possible wave function looks something like this, right? It's kind of like a standing wave in the box between 0 and L. Okay, and this is basically the wave function for n equals 0. And what I'm plotting here is the modulus square of the wave function. So the probability of finding the particle somewhere in this box. Okay, so, and I know, of course, that the particle must be somewhere. If it's in there and I integrate over the length of the box, then I must find probability 1. So modulus square of the wave function, okay, integrated over the length of the box must give me 1. Okay, so that's fine. That's fine. But now, what happens if I do this? This is like a little trickery. Okay, so I'm going to put a barrier there. Okay, let's say I can do that. I'm not saying that this is possible, but you know, let's say hypothetically we can do this. So what would happen then? Well, I can, if I put a barrier, I can, you know, pull these 2 parts away from one another. So let's say I put the left side to the left and the right side to the right. I put them very far away. Okay, so then if I would calculate the probability of finding the particle on the left side of the box, I would find half. Okay, that's you have like half chance, so 50% chance of finding the particle on the left side of the box, and consequently, there's a 50% chance of finding the particle on the right side of the box. Okay, but now the interesting thing is very, very interesting to talk about, and that is the fact that if I do a measurement, okay, I do a measurement, let's say I put one electron in a box like this, I put a partition in there and I pull this left and the right apart, very far apart. Okay, let's say one half of the box is let's say here in Irvine, the other half is somewhere in Australia. Okay, I'm going to put them on a plane and take it there. And then I'm going to say, let's open the box number 1 and see if it's in there. Now, there's a 50% chance of finding the particle in the box. There's no surprise. Okay, so 50% chance. So let's say it's either 0 or 1 chance of finding it in the box. All right. But the problem is, if I do that and I find the particle in box number 1, then I know immediately that it was not in box number 2. Okay, that sounds trivial. And if it was not in box number 1, then I know immediately that it must have been in box number 2. But these two boxes are very far apart. And in fact, I can take box number 2 and move it all the way to the other side of the universe, and then open up box number 1, look in it, and if it's not there, I know immediately that it is in box number 2. And that is weird, because I know some information that is instantaneous, okay, about box number 2. I open box number 1, and instantaneously I know something about box number 2, which is on the other side of the universe. That means I'm transferring information. I have information about something that is very far away. That is information transfer that is basically moving faster than the speed of light, okay? And this is a very interesting problem in quantum mechanics. It's a problem of non-locality, and that means that there's superluminal transfer of information, okay? And that violates the theory of relativity, because it says that nothing can move faster than the speed of light, okay? And that is kind of a very interesting conundrum for many people who think about quantum mechanics. This is different from the classical case. Classically, the particle is deterministic. It's either in box 1 or in box number 2 at all times. And it's just a matter of chance of finding it in box number 1 and box number 2. But quantum mechanically, we don't know, okay? It's purely probabilistic. There's definitely a chance of 50% before you open box number 1 that it is in box number 2, right? But after you open the box number 1, there is no chance left, and you have revealed the answer. So probabilistically speaking, you have found the answer. It's not deterministic, it's purely probabilistic. And that is the main difference between classical mechanics and quantum mechanics that is sometimes confusing to people. So this is a very well-known problem. It's actually, Einstein did not like this at all. And he kind of said basically, you know, quantum mechanics is incorrect because of this. All right, and he called it spooky action at a distance. All right, but let's get back to our retinal molecule, because we have some answers to give. So we have an expression for energy. Remember, this was the expression. Let's put it down. Make sure we are on board with this. The energy expression, the general energy expression was En equals n squared h squared, and then over 8ml squared. Okay. So, and now I'm plotting the energy levels for n equals 1, 2, 3, 4, 5, and so forth. Okay, that's what I'm doing. I'm just filling out. Why? Because I have numbers. I know what h is, 8, m is known, and the length of the box is known. Why is it known? Because I know the length of the molecule. Okay, there's 10 carbon atoms involved in a pi conjugated network. I know the length of the bonds in between. There's 9 bond lengths, and so I can calculate what L is. So I can determine the energies, the states in which this pi electron can sit. And you can see here very nicely that there are different states in which the particle can sit, all right? And that they're separated from one another. Now, where is this particle situated? Well, I mean, we have to see how many electrons do we have, okay? We have 10 carbon atoms in the pi network. Each carbon atom contributes 1 pi electron. That means there's a total of 10 pi electrons in this network. So 10 electrons will have to accommodate these states. So if we do that and we take care of the fact that there's a Pauli exclusion principle, we can put the electrons in this system. Okay, so that's what we're doing here. We put 10 electrons, okay, the maximum number of electrons in one state, of course, is 2. That's Pauli's exclusion principle. So I can make 5 pairs, and the highest occupied state is n equals 5. All right, the lowest unoccupied state is n equals 6. So now if I'm going to excite, let's say, an electron from state n equals 5 to state n equals 6, I'm going to make a transition. Okay, here it is. All right, and there's a transition energy, and I can calculate what the transition energy is. All right, it's the difference between level number 6 and level number 5. And I have expressions now for that, because that is basically h squared divided by 8ml squared, and then 6 squared minus 5 squared, right? So I can compute that, but of course I need to know what L is, so let's do that. L is going to be 9 times the average bond length of carbon atoms that are part of a conjugated network. It's about 140 picometers. All right, so 9 times that will give me an actual number. Plug in this L in this expression, and then calculate. So this is the expression I'm going to evaluate. I know what L is. I know what 8 is. M is the electron mass. H squared is something I know. 11, of course, something I know as well. And then what I get for the transition energy is 4.17 times 10 to the minus 19 joules. That is the transition energy according to this model. Now, the big question is, does it make any sense at all? How true is this model? Well, we can compare, of course, the result with the actual transition energy because the absorption spectrum of retinol is known. Okay, so I can convert this to wavelength. Let's do that. That's an easy calculation. H times C divided by the energy gives me a predicted absorption wavelength of 477 nanometers. Okay, so 4.77 times 10 to the minus 7 meters is 477 nanometers. So let's look at the absorption spectrum of the molecule retinol. Okay, here it is. Oops, that's an interesting little mistake there. This should be nanometers. Okay, so here it is. The absorption spectrum is about, the maximum is about here. So let's go down, over here. So it's about 320 or something according to this, spectrum. And the answer is, what I found is 477. So clearly it's not the same number, but let me put this in perspective. This model is, of course, a little bit crude. Okay, I simply said this is a one-dimensional system, and I put an infinite barrier there, so it's kind of like a little hand waving there. Yet I'm ending up with an answer that is definitely pretty close. It's the same order of magnitude. It's not completely way off, right? Like orders of magnitude wrong. I'm pretty darn close, right? So this model actually is a fairly good description of what's going on, right? It's a fairly good description of pi electrons in the system, and it kind of explains the color of the molecule. The absorption spectrum of the molecule, of course, relates to the color of the molecule. So let's have a quick look, and I really like this because the transition energy depends on the molecular length L. So this is the retinol molecule, and like I said, it's about 320, 330 L max, and experimentally we find something that's slightly longer, but it's still pretty close. Okay, so let's look at this general expression for transition energy. We see L here again. So let's look at a molecule that has a longer length, right? So a conjugated molecule like retinol, where the conjugation length is longer. In that case, this L here in the denominator, it's going to be a larger number. That means the transition energy must be less. Less energy, of course, means longer wavelengths, right? There's an inverse relation between energy and wavelength. So that means if I find a molecule like this, beta carotene, look at beta carotene, much longer conjugation length, right? You know beta carotene, of course, it looks like an orange color. And that means indeed that the absorption maximum is shifted to the red. It's 460. So that is a significant shift by more than 130 nanometers relative to retinol. And that is kind of consistent with this pretty simple model, pretty simple quantum mechanical model that we developed. So this model really kind of brings out the essence of transitions in molecules, right? Transitions in molecules that explain the color of these molecules, their absorption spectra. It's pretty good. It's not perfect, but it's pretty good. It predicts the trends, and it basically gives us some physical understanding of these processes. Finally, just for fun, let's look at what retinol really looks like. It looks like a yellow powder in this case, okay? And beta carotene, of course, is orange, right? So beautiful molecules, very colorful, but the colors really come, of course, from the excitation, the quantum mechanical excitations of these pi electrons in this conjugated system, right? That is basically what gives it color. And so I find this really, really fascinating. So that was my first foray into a quantum mechanical application in chemistry, and we will continue, of course, with talking about atoms as we go along. All right, I'm going to leave it at that, folks.